Okay, so let us start. Okay, hi everyone. Thanks for joining this session. So, hope you understood what is the topic of this today's session. So, this is a part of project-based learning. Uh, the first one I'm taking as a UART design. Okay, which is a serial protocol, which is like very standard and old protocol used for serial communication. Okay, the reason I take this is like it's easy to implement this kind of thing, but yet it will have its own complexities. So we can as we go learning these things, right? We learn the protocol and as well as other language constructs like SystemVerilog, how we can use and other things. So the purpose of this course is like I want to teach you something different than compared to others, right? So I want to show you the process of designing. Like you have a concept, and where you have to think through the specification and different implementation details and other things, right? So even before you attempt to uh, do something in the code, you should understand thoroughly what is going in. But at the same time, given the complexity of the designs, right, you cannot understand everything of the design in one shot. So you have to go layer by layer, like step by step. Okay, so somewhere we have to start. Uh, like we cannot understand whole specification in one shot also, right? So we have to go take something and implement and understand, refine our understand, um, and then try something else. Okay, and make sure we are in the right direction. Okay, so at every point we try to build models. uh, this model can be a simple waveform or some complete simulation in some other language, like say I'm going to show you the Python based things, which will give some flexibility. Okay, so even before you attempt any Verilog code or system Verilog code, you have to understand lot many things before going there, right? So that's what that is the background of this course. Okay, so in this session, like I will introduce the UART protocol and what is the motive behind that. And in this session, we design some simple module in this whole design. Okay. In next sessions, as per schedule, we will show the demo of the other things. So I said like this is a project based. So I go through. I mean, I will take you through the process of the design. Okay, I will code before you and see how it goes. Okay, so I want to show the thinking process. Say we do some mistakes and how to rectify, how to go back and see, and how to correct our understanding. All those things I want to show you. Okay, it's not any pre-planned one. Okay, I have few code snippets, but mostly I will do a live session. Okay, so yeah, so the approach here is like it's a guided design process. I will do the coding in SystemVerilog, Python, many things I will show you. Okay, so the emphasis is on like how I take the problem and think through it and solve it. Okay, so in this like design side, we are going to use SystemVerilog. I mean, Verilog or SystemVerilog, it doesn't matter because today the standard is only SystemVerilog. There is no separate Verilog. Okay. Uh, and to verify this, I'm going to show you some Python-based test bench, which will be like very simple only. There is no complex things in it. But yeah, like once you do one example, you will also understand. If you have a right environment, you can also do the same. Okay. Yeah. Now let us go to the actual design. Like UART is an acronym for Universal Asynchronous Receiver and Transmitter. Okay, it's a protocol where the communication is serial and it happens asynchronous. When I say asynchronous, the both parties who are participating in the communication, they don't share any common signals except the data pin. Okay, say like a clock. Okay, both will have different clocks. Okay, that's where this asynchronous means. Okay, only data lines will be shared, I mean connected between the receiver and transmitter. Otherwise, every uh, every block will have its own clock or clock frequency. It doesn't matter. Okay, so these are used in embedded systems mostly, where you required let's say low rate communication, but at where you cannot have a parallel buses. Okay, so this is a serial bus. That means at most you required only one wire connected from one device to another device. It's only one wire. Okay, so that will simplifies your most of the logic. Okay, which is going between two modules. Okay, so yeah, the basic operation between these two, I mean any modules which connected serially are through TXD and RXD pins. Like TXD is the data pin used for transmission, like it's output of one module, and RXT is the receive data pin. Okay, which which is the input to the module. So if there are two modules, okay, both will have TXT and RXT. Okay, so they are cross coupled each other, like one module's TXT is connected to another module's RXT and vice versa. Okay, yeah, so the communication flow is like you have a bunch of data to send from one place to another place. Okay, say one module to another module. One could be a serial, I mean, one could be a CPU, which one tries to talk to some other remote CPU. Okay, so in both cases, like both computers will have a serial interface. Okay, say earlier we have right telephone lines were used to connect between two computers. Like, okay, so there this UART is the key module where only you will have a single line along with other some lines, which in this module we are not going to um, touch those things. Like they are called modem signals. Like the moment you like hang the receiver, right, you will listen to the ringtone and other things, right? So basically all are electrical signals which tells whether line is there or not. Other computer is also available, some things, but here like we assume a line established between two modules, and they agree upon a protocol, like how many bits to transfer, what are the parity, those things. Like we assume both parties understand, I mean agree the same protocol. Okay, then start communicating. Okay, so yeah, everything like we split the data into bytes, like which is 8-bit wide. Then we do a parallel to serial conversion and send it over the TX lines. Okay, so it will have its own frame format. Like we are going to look that what is that format. On the other side, the reception will happen like it take the serial data and do some like reframing and convert into the parallel data. So that's what this deserialization means. Okay. So, but since they don't share any clock and other things, right? It will be a tricky for the receiver where to start. Okay, you don't know, like because both clocks may be out of phase or maybe completely running at a different clock periods, right? So the hardest part compared to the, I mean, compared to other modules is the receiver design. Okay, so here you learn like what is the UART design and how it looks like inside, like what are the modules and other things. And as we go and code, like we'll see some SystemVerilog concepts, okay, best practices and other things. Okay, and similarly, how you can implement a AXI-Lite interface. But here we are not going to write a complete module. Okay, we will use other tools to generate this AXI-Lite interface based on our register definitions. So in industry, like no one directly write AXI-Lite, of course. Mostly like while studying, you need to understand how it works and other things, but normally we don't write because it's a standard interface. We already have many tools, like both open source, commercial tools, and many things are there. So we simply use those tools. So here also we are going to use a Corsair register tool generation. I mean, register generation tool, which is free. Okay, so we are going to use that. And after after generating all these designs in Verilog, okay, we are going to verify this with Python test bench. So here we are not going to do any uh, kind of verification, but simple verification methods we can do. Okay, so which is not very hard. Like I will give the all the code once this session is over, so you can also practice and understand the design. Okay, so yeah, here I go through the step by step, and I code live. And if you have any doubts, you can ask me why we did the way I do. Okay, and there are any design decisions like we can see. Okay, so yeah, to understand, right, like we need to understand the protocol at some level. Okay, we write some small module like behavioral model, uh, and simulate it and check the waveforms, then understand, correct our understanding. Many things we'll do, right? So I'm going to use again Python for that modeling. Like I will show how to do and understand it. Then we can continue with our design. Okay, so yeah, I'm going to show you a block diagram, but here the key components are like Baud generator, transmitter, receiver, and control registers. Like this control register module, we say like control and status registers, so which is called CSR. Okay, and yeah. Okay, so this is the like overall how it looks. Okay, there is a transmitter and a receiver, and say like uh, there is a bunch of data to send from transmitter to receiver. Like it will receive on a parallel data interface, then it uses TX and RX pair and send it. Okay, so here I am showing you um, the frame. Okay, how it looks like, since this is one single bit, right? So it can toggle anywhere, but what it transmit, we should understand, right? So this is the frame. Okay, where in the ideal case the line will be high continuously. Okay, then suddenly like transmitter start transmitting, then you will have a start bit which is a low for one bit period. Then you will have a number of data bits. Here I am showing 8 bits, like D0 to D7. Then again there is a optional parity bit. This is optional, like you may have or may not have. And again there is a stop bit which is a low. Okay, after that again the signal will be high, like okay, which is like idle. So with start and stop in between data bits, like we transmit this thing. Okay, so here this is a very low frequency communication. So we say like how many bits are transferred per second, that is called baud rate. Okay, baud rate is defined as a how many symbols transmitted per second. Okay, so in this protocol we don't use any complex constellations to transmit. So here the one symbol is one bit. So you can say for UART protocol, baud rate is same as bit rate. Okay, typically the like earlier modems have a baud rate of 9600. That means like every second you can transmit those many symbols or bits. Okay, uh, Okay, transmission wise, it is very easy. Like you have a period, okay, which tells the when to send the next bit, okay, and you just start, transmit the data pins and stop. Okay, that is enough for a transmitter. It's very simple design. But on the receiver side, okay, it keep on getting some highs and lows on the RX bit, okay, but you don't know where to start and where to stop and where to sample those things. For this UART design, they decided, right, so you sample the line at very high frequency, say like 16x, okay, so your bit rate is something, okay, but you are running at a very high, I mean higher frequency, like which is 16 times greater than the incoming clock frequency, I mean data frequency. And we see the start, we sample the start, and we keep on aligning the sample bits, okay, when to sample. So we carefully align that sampling to the middle of the bit width, so that the chance of getting correctly will be increased. Okay, here we are seeing, right, incoming data, sample data, bit pulse data, which are centered. Okay, so that for that, like we require some state machine go through the data line and sample it correctly. Okay, there it can go many errors. Incoming data frame will be corrupted. Since it is electrical line, you can see all the all other errors also, right? So like on receiver side, it should detect the error conditions, framing errors or parity errors, many things. Okay, something like that. So I think we have understood the basic protocol and framing, frame of UART frame. So yeah, here I'm going to show you the relationship between the baud rate and what is the clock frequency we use and some divisor. Okay, so this is the formula. Okay, so on right hand side, you have a clock frequency, which is the actual clock at which we are running the module, and left hand side there is a baud rate. So the conversion from the baud rate to the clock frequency, like we have fixed clock frequency and we have a baud rate. So to achieve this thing, what is the divisor we want to calculate? It's a counter, it's a 16-bit counter. So we have to derive, I mean use this formula to get that divisor correctly. Okay, but only thing, like both transmitter and receiver knows is only baud rate and other framing thing. Okay, how many bits are there, but they can use their own clock frequency. That's where this asynchronous thing comes, right? So typical, say like I am assuming we are running at 100 megahertz clock. Okay, then these are the, like for different baud rates, these are the 16-bit divisors we are going to use. So I just put in a table, like it will come handy. Uh, but we are like we use it this formula only. Okay, so yeah, this is the example calculation, which is like for baud rate of 9600 symbols per second. The divisor will be 651. Okay, which is the nearest integer. It may have some slight error, but it is recoverable. Okay, so it will not create any errors. Okay, so before going to that, yeah, we figure. Okay. Yeah, we want to go to the specification of the actual like the module. Let me go to the specification. Yeah. So this is the like cut down version of what we have commercially, like because in this simple project. I don't want to put too many concepts. Okay, so yeah, as I told, it's a serial protocol which is asynchronous between transmitter and receiver. Okay, so we are going to support multiple baud rates. That's where that divisor register I showed, and the data format, like number of bits, can be 5, 6, 7, and 8, and the parity can be like even, odd parity, even parity, or no parity at all. And yeah, and there will be stop bits, like you can have one or two stop bits to make sure like you are completely uh, frame. And inside transmitter and receiver module, we'll have some FIFOs to store some 16 byte data. Okay, so that like you can do more transmissions. Okay, otherwise what will happen, unless you transmit one word, you cannot send it again. I mean, so unless it is finished. Uh, yeah, but we're using FIFOs, you can keep on receiving, and still because compared to hardware, software will be relatively slow, right? So you may get very high speed data compared to CPU. Okay, but CPU can CPU means like software can read it at different time whenever it can do. Okay, that's where these buffers, FIFOs, will be helpful. Okay, so as I told, like these two are the configurations, like how, what is the baud rate and data format. These are the configurations which both parties agree before doing any transmission. These configurations can be done through AXI-Lite. Okay, that means like in in these days we mostly use ARM based designs only, right? Where this AXI-Lite and AXI are the very common protocols which we use for configuration. Okay, so in this project we are not going to touch any modem signals. Okay, and interrupts also. Okay, so interrupts are like once we receive data. Okay, it will inform the software that it received the data, or when you transmit something, if something occurred at the line, like say error. Okay, it should inform the software, and it should raise some interrupt. Okay, so but in this project we are not going to do any of these things. Okay, then yeah, like we can go through the register map. Like I made it a very simple register map. Okay, after removing all interrupts and other things, right? So we can so I defined only four registers. Okay, so the first register, like by the way, all are 32-bit registers. Like in original spec you can see they are like 8-bit only, but yeah, we are going to define as a 32-bit registers, where like still we are going to use 8 bits only. In that, rest of the 24 bits are just reserved. Okay, so these are the four registers we have, like RxD and TXD. Like these are the data registers. This is the data register, but internally they are like separate registers, but both are addressable at the 0. Okay, like in next session I will explain what it means. Then at C address, there is a line control register which will actually configure the frame, data bits, and other things. Okay, and at 1.4 address, like there is a line status register which tell what happened to the transmission, any errors occurred while receiving or transmitting. Those things is okay. And last register is at 1.8, which is the divisor for baud rate. Okay, so for a given clock frequency, what is and baud rate, what is the divisor? We have to calculate ahead, and that value we are going to program in this register. Okay, so yeah, coming to the first register, this since we are telling like max 8 bits per word per byte, right? So That's why we have a 0 to 7 as a data, and rest of the things are just reserved. Okay. When you read this address, that means like we are once you receive the data from some other transmitter module, when you read this, you are actually reading the FIFO, like a receiver FIFO one by one. Okay. Similarly, when you want to transmit, you write that data to the same location. Okay, to push into the TX FIFO. So writing will do the transmission and reading will do the reception. Okay, receiving. Okay, that's why. But we are sharing the same address location for uh, both push and read. Okay. Then line control register, like we have defined, these are the bits. Okay. So first two bits will tell how many bits per character defined. Like yeah, I didn't mention here. Like zero of the zero value means 5. From there, like 1 is 6. Okay. Uh, two is 7, and 1 means 3 will be like complete 8 bits. Okay, so then there is a single bit. Okay, which will select how many stop bits. So default will be 0, that means only one stop bit. If it is set, means we will have two stop bits. Similarly, like parity enable bit will be there. Like if this is 0 means there is no parity at all. Okay, if it is 1 means we'll have a parity enabled. Okay, next bit will tell like what kind of parity. If this is enabled, then only this parity has a meaning, otherwise it's a reserved. Okay, so if we set I think we have defined definition here like of the parity. So if it is 0 means odd parity, and 1 means even parity. Okay, yeah, next register is line status register. Like these are the different bits defined for the status. Like first bit is data ready. Okay, that means like once you receive from the other module, right, this bit should be set. That means you have some data to read, then software will go and read the first register, which will give the actual received data. Okay, before going there, like it should confirm it received the error free data, right? So say overflow errors and parity errors, like framing errors, many things. Okay, like even FIFO errors. Okay, all those things are defined here. Okay, like we'll see what it means, like why when we are actually implementing these things. Okay, so and last one is, as I told, like it's a 16-bit divisor, like which dictates the like clock frequency to the baud rate relation. Okay, so like in the above things we are telling like some how software access those registers, right? So those definitions were here. Like read write is a regular register where software can read and write. Okay, similarly read write one to clear, read write one to set. So it's like when it writes one, that means like in next cycle it will be cleared. Okay, so and similarly write one to set means if it write once, it will set the bits. And read only on clear. Yeah, other stuff was like we'll see how we are going to use it. Okay, so as I told, like we are going to implement only these 4 registers, which is very simple to implement. Okay, so then we can, okay, protocol we have seen. These things also we have seen. Okay, yeah, so this is the block diagram we are going to implement. Okay, so where on one side we have an AXI-Lite interface, and there is a clock pin, and along with the reset also, which I didn't show. Uh, and there is a TXT, which is for transmission, transmit data, and there is an input pin for RXT for reception. Okay, so these pins will be connected TXT is the output of the UART TX module. Okay, in turn which will it will receive the baud rate and other signals from the baud rate generator and the configuration from the CSR module. Similarly, RX module will have input from the RXT and it will have other configurations from the CSR and the clock and reset, and again a baud signal from the baud generator. So in next sessions we will show what are the actual namings and other things, but as of now just I made it very high level, this black thick lines are for configuration and blue line is for clock, and rest of the things are like other signals. Okay, so yeah, today's session just I want to introduce the specification and protocol, and I want to show you like a simple baud generator design. Okay, to understand the actual like how we are going to use these tools. So this will set the base for next sessions, like where we are going to design the transmitter and receiver. Okay, so yeah, like before going to demo, anyone has any questions? Okay, so yeah, I will continue with this thing. Okay, so here the like I showed, right. So this is the one we are going to design for today, and this UART TX in the next session, like next Thursday, and RX will be on third session, and integration of the entire thing will be on the last session, like where we are going to integrate the entire module and test it. Okay, so here the key things are like how we calculate the baud rate, okay, and the divisor, and we'll get the divisor from the AXI-Lite register, okay, and then implement the baud generator in the variable. Okay, so that baud rate calculation and divisor calculation as per that table we have showed, right. So we'll do that. Okay, so we'll use the AXI-Lite to configure that divisor, okay, which holds the divisor value unless you write another value. Okay, yeah, so I'll show you the demo. So, so I'm going to load my environment. Okay, so here in this thing, okay, we can use the same area for each also. So I can just create UART.sv, which is the top module, and a make file to run the compilation and the simulation, and then we'll have a test bench, Python test bench for this thing. Okay, so this Python test bench will be like very simple code. Okay, you may not require like much. Okay. can use the code and later we can understand. Okay. Yeah. So inside UART, we are going to do Baud, right? Baud gen module. Okay. So we have like these files, like two SV files and one make file and one Python file. Okay. So yeah. Okay. So let us with this thing module UART. Okay. We will define ports later here in, in modules as a guideline. Like we use this construct, like after end module we end it with the colon and the module. Okay. So then we have block pin, and we'll have negative sensitive, I mean, to low reset. Then here actually we'll have okay, we can define tx, okay, which is output, txt I mentioned, and rx, which is the input. Okay. Then we have another interface which is AXI-Lite. Okay. So which is like whatever the block diagram we are showing, like those things are. Okay. So I will fill this AXI-Lite interface later, right, when I generate the actual AXI module. Okay. Okay. So yeah, once we define that AXI module, I will AXI-Lite register modules. I will instantiate here. Okay. Then here, first step is like Baud gen Baud generator module. Then I will have a TX module. Then I have RX module. Okay. So every week as we go, like we'll do one by one. Today we are going to generate and instantiate these two modules. Okay. So this is how like we will build the complex design like step by step, instead of going everything. But at every step we are going to test each thing, right? So that like we will gain confidence as we go. Okay. Let me open the board gen thing. Okay, that module. Okay, so okay, which will take uh, input clock, then reset, then actually 16-bit divisor. Okay, so then output, yeah, I will name it as a Baud output. Okay. So like we have a input side clock running at 100 megahertz. Okay. Running at 100 megahertz, and for a given baud rate, we decide what is the divisor value to program. Then this module should generate a baud signal, which is 16x higher than the actual requirement. Okay. So this is like we define this thing. So I'm going to instantiate this thing. So these are the clock and reset, and this divisor and Baud, maybe we have to declare as a local. So let's, yeah. Okay, with this thing, right, we prepared the base. Okay, we prepared the base and other things. And next, I will generate the AXI-Lite register module using register generation tool. Okay, so for that, what we required is one more file, which I am going to create. Okay, so UART slave dot so I'm going to define my registers in the JSON format, which is the input to the tool. Okay. Again, CSR config. So CSR config is the input to the tool. These two are the input to the register generation tool. Okay. So then I will show you what should be there in the JSON. Okay. So I have a sample. I have a sample register definition for this thing. So I will just go through that. Okay, so I think we are going to use the AML, like YAML thing on the JSON. Okay, so which is like I prefer AML because you can have a clear understanding under what section what are there, and you can have comments also. Okay, this is the file we are going to, and I have a sample. Okay, so this is the entire registers we defined in the spec, but here I am going to just take, in today's session we are not going to generate all the things. Okay, so I'm going to generate only divisor. Okay, so this is defined as address 18. Okay, so here I can just explain you what it means. Okay. Okay. So in this AML, like top level is the reg map. Okay. Under this, we'll have register definitions. The first level is the name of the register and the description and the address. If you have a multiple bit fields in this register, like this is the place we have to give. Like here we are not going to use all 32 bits, right? Our divisor is just 16 bit, which tells that it is 16 bit, and the least significant bit starts at 0. That means combining with the LSB bit, this uh, this will be like 0 to 15. Okay. So the axis for this register is like a read write. That means software can read to register and write to this register. And the hardware axis, that means from the CSR module, this will be the output. Okay, which is we are going to connect to the Baud generator. Okay, so similarly we have to do the config. So I will copy this thing. I will copy this thing. Okay, so here these are the global configurations. Okay. So by the way, like I will explain what these means in the next things, or maybe separate video I will put in documentation. But as of now, like we are going to generate the registers using the register generation tool, which will be which I am going to show you. Okay. So the name of the register part is what we have showed. It's the name UART slave. Okay. Okay. Currently, we are not going to generate any documentation. Okay. So we are going to generate only Verilog module. Okay. So we tell what is the base address and what is the data bit, which I told like 32 bit, and the address bit, like how many required. But I took like 16 bits because we have only 4 registers, right? And these things will be aligned with the data bit, which is 32. That means the address key is like 048, like that. Okay. Then yeah, reset we are going to use. We defined as a like act to low reset, right? So we are going to put the same here. So make, so it's a synchronous and a negative reset. Okay, act to low reset. So with this thing, uh, so we have a AML file where we defined only one register, defined at address 18, and we defined the reset as a synchronous negate, and yeah, that's it. I can save these things here. Yeah, maybe UART slave.v. Okay. So I'm going to generate the registers. Like before going, like here we don't have anything else, right? So maybe I remove JSON. Okay, we have these things only. Okay, we have SV files and yeah, YAML and CSR config. Okay, so Corsair is the actual register generation tool. Okay, which takes this YAML and CSR config files and generate the module files. Okay, yeah. So generated the actual Verilog file at this place. Okay, so we can see what it is. Yeah. Okay. Okay, so the left right hand side, I opened that generated things. Okay, which will have see, this is the AXI-Lite interface signals, and clock and reset were there, and only one output from the CSR, like it's a Divisior. Okay. So yeah, we can copy these same things uh, for the AXI-Lite, so that like, we can connect the same names. Okay. This AXI-Lite interface is the top level AXI-Lite interface, so that like we can connect to the AXI-Lite registers. Okay. Here I am going to instantiate this UART AXI-Lite slave. Yeah. One more thing, like here it uses the parameters, right? Those parameters maybe we can just copy from here and put into our top module parameters, so that like these input and output it gives the same parameters. Okay, so we are going to define the other signals. Okay, where we connect mostly all. Okay, but except few things like this reset name is RST. Then we have all other things, but the divisor name is this one. Okay, so we have connected the clock reset and the divisor output and the AXI-Lite interfaces. So with this thing, like we finished our AXI-Lite registers, and we just instantiated empty Baud gem module. Okay, so yeah, so we can compile this thing using the Python basic test bench and see if any errors occur or not. Then we can see how to implement the Baud generator module. Okay. Yeah. So I'm going to fill the make file. Okay. So where I defined the top level module as Verilog, like same as like even if you are using SystemVerilog also, like we have to mention Verilog. Then the simulator as Icarus, but I'm going to use Verilator because Icarus don't support all SystemVerilog constructs. Okay, so and these waves will tell like whether we want to see the waveforms or not. Okay, so then okay, then we are defining some other variables. Uh, our DUT is like UART, right? UART, and top level is also UART, and this one is test trigger. This module is nothing but our Python file name without extension. Okay, so our Verilog source file is here, but yeah, maybe instead of these things, I can just so that like there will be no confusion. This is one module. Similarly, we have many other modules like files. So I'm going to define all the source files. Like one is here, and another is I think Baud. We have currently we have only these three modules, and we can so I'm putting some other variables related to the validator compile arguments. Then we have so I will share all these files like so that like once you know what to write, it's very easy when you are creating new files. So it's like they follow rules on it, so you don't need to put much thinking here. Okay, so you can just copy paste all the files. Okay. Next thing is we have to define the UART module. test. So here, okay, I am importing the required packages. Okay, so CocoDB and clock related packages. And here we are going to use some extensions defined for the UART. Okay, it will be very simple. Like once you see the example, you understand. It's not very complex thing. Okay, so what we can have is a simple CocoDB test here. Okay, which we defined. Okay, hello world. Okay. So here my intention is just to see whether our modules are compiling without any errors or not. Like I'm not going to test anything. Okay, so we can see if we face any syntax errors and other things. So I'll just do the make. Okay, so show some error. Okay, so saying some module was not formed. We will see what is that. So we have named it as a AXI-Lite only, but I am not sure why it is. Okay, input. Okay, input side some error. Okay, yeah, I understood. This is like we missed one comma here. Okay, yeah, that's why it is error. Yeah, after this session, I will give all the environment and other stuff to you, so you can practice this thing. Like then you appreciate what is like. Initially, if you don't know about these things, right, you feel daunting. Okay, but once you started doing all these things, right, because everything here is like a free tool. Okay, you don't need to go for any commercial tool. Okay, so yeah, you can learn these things in one or two sessions. Then you can use these things in your regular design. Okay, it will help you to build any complex design. Okay, with small steps. Okay. Okay, so it says pass that, but since we don't have any test here, that means our source files were without any syntax, and we are able to compile. Okay, so yeah, then what we can do is we can go and implement this Baud generator. Okay, so I'll, I'll show you what it means. Baud gen, I'll open the site. Okay, so we have an input clock. Okay, we have an input clock. Uh, the output is a Baud underscore O, okay, which is like we run a counter, okay. Let me define that 16-bit counter, okay, which is a free running counter. Initially, this will be initialized with a divisor value, then it will do a countdown. Once it reaches zero, okay, once the counter reaches zero, it will give a one cycle. I mean, it will asset the Baud out as a one for one cycle, and thereafter it will keep a zero. Okay, so that means like say the divisor value is 16. Okay, so we load the value, counter value with the divisor like 16, and from there it starts countdown like 15, 14 till 0. Once it reaches 0, counter value again goes back to the 16. But at the same time, in that particular cycle, that Baud out will be one pulse. That means like we are for every clock 100 megahertz clock, so every 16th cycle we are generating the Baud output. Okay, that's what this Baud generator means. Okay, so we are going to generate. Yeah, I am putting the synchronous reset only. Okay, okay. So before going, I think we should know when to load this divisor value, because it's a free running counter, right? We don't know when to stop. Okay, so there should be another input, okay, which is load divisor. Okay, so once, so we can have another, and if load divisor, you can load the counter with the divisor value. Once it reaches zero, again we can load or I can say we'll implement this load divisor next time. Next, this thing. Okay. Every time the counter reaches zero, it will load the divisor, counter with the divisor, and thereafter we keep on decrementing the counter value. And okay. Now, like this is the free running counter. Like at any point, this counter value is loaded with the divisor and keep on decrementing. Okay, once it reaches zero, again it will counter from the divisor. Okay, so the Baud output will be like I can assign the Baud output. Once it reaches the zero, the Baud output will be high. Okay, this will be like only one for one cycle, because thereafter it will again generate and load with the divisor, right? So it will be only one. Okay, let us see if we can just, yeah, whenever we change the RTL, it will take some time for compilation, but If you don't have any change in the RTL and only change in the test bench, like Python test bench, it will be very fast because you don't compile it again. Okay, so we successfully compiled the thing. Yeah, let me close this thing. Okay, so we will see the waveforms actually. Uh, so instead of I will just write a test for Baud gen simple test. Okay, so here I'm directly going to change the divisor. We can go back to the document and pick one of the divisor. Okay, so here we are going to pick for baud rate 96 9600. For that, the divisor value will be 651. Okay, so we are going to load the divisor 651. Okay. Instead of instead of writing a register, I'm going to directly configure that. Okay. For the 9600 baud. Okay. So how I'm going to do this is I can access the internal signals like DUT. Our signal is divisor, right? So I can just put that. For that value, we are going to put 61. Yeah, 651. 651. Okay. But to run the thing, we required a clock, right? So here I'm generating the clock with 10 nanoseconds. So 10 nanoseconds is nothing but 100 megahertz. Okay, so 10 units are nanoseconds. So which is like 100 megahertz. Okay. So we just configure the divisor directly by using the signal hierarchy, and then we started the clock. Okay. Similarly, we required a reset also. Okay. For this, what I can do is just use directly reset RSTGL. Okay. So I will let's say value to 0. Then I will wait for some 100 nanoseconds. Then I will release the reset. Okay. Okay. Then what we can do is simply wait for another 100 nanoseconds. Then we can see the waveform. Okay, how that baud signal was generated. Okay. for this thing I will just so I want to see the waves, so I'm setting the waves. Okay. Since we didn't change anything in the RTL, now this time the compilation will be fast. Okay, so it says like fast because we don't have anything else. So now you can see we didn't get the waveform actually. Let me check the file one. Maybe again that yes, here. Mm, just to and we have some more variables here. So, these are the like typical time units we put right in the Verilog time scale 1 nanosecond by 1 nanosecond, so something like that. Still, we didn't get the waveform. Yeah, this time it is trying to compile with the trace ST enabled. I hope this time we'll get the waveforms. Yeah, now we got this dump .fst. So you may have had a VCD format which is like open source. You can open with this. Uh, so similar to that VCD, we have FST file which is fast signal trace. Okay, fast signal trace is another waveform format which you can use with GTK wave. Yeah. So okay, so this is the, so we have not done anything on AXI-Lite, so we can directly go to Baud gen module where we have very small set of signals. Let us see how it works. Okay, so this Baud was high because this divisor signal is kept at 0 only, though I expect this to set to the 51 651. Let me check. So in the DUT we have a divisor, okay, which we have set to this thing. Or we can go to one more level directly into input. Okay, so CS class. Let us load the waveform again. Okay, so which will work. So I think we can use instead value. There is another thing called set immediate value. So the simulators will work, right? How they work is like it do a step. Okay. Maybe because of that, it is trying to avoid that step. So without waiting for any simulation step, like now we update the divisor value. So even at the like very first few steps, this value should be set. Let us see if this is set here. Okay, somehow this divisor value is not set. Okay, what we can do is just I want to show before going to the. Okay, okay. I think this was overwritten by this CSR value after while. Okay, that's why it is becoming. Okay. So what we can do is default baud rate we can set in the our register. Okay, say 651. Okay, so then we don't need to configure this here. Okay, so from the register after reset like a default. So we don't need to change anything, just the default file, I mean the register value will be updated in the other file. Yeah, meanwhile, if you have any doubts, we are towards the end of the session, right? So maybe you can just ask me. I can try to answer. Yeah. Okay. Now you can see the divisor value is updated. This is in hex, right? So I think you want to see this one. So yeah, the default is 651. Okay. Yeah. Since we just ended very few cycles, right? So we are unable to see that. We can just increase that because the count value should go high, right? So what we can do is instead of we can wait for 100 microseconds so that it can reach there. Yeah, so the baud rate 9600 is very low. Okay, that means like we have per second 9000 signals only, right? That's why we have to wait for like microseconds to actually see the waveform. Yeah, now you can see, right, for a baud rate of 9600, so we'll get a baud signal for every, say, let me calculate that. 9000 means, say, roughly 10,000, right? Which is like how many? Uh, which is like the difference between the time period between each pulse is around 100 microseconds. It will be less, it will be more than that, but like roughly for a 9600 baud rate, this will be that. Okay. But since we sampled this at higher, I mean 16, right? We sampled this as a 16. So like 100 microseconds divided by 16. So that is like 6 microseconds, 6.25 microseconds. So we can, I think we can see this. Every pulse has a difference around 6 microseconds. Okay, so yeah, that way, like we by default from the AXI-Lite register we define this thing, but let us change that through AXI-Lite. Okay, then we can conclude this session. Okay, so run extension AXI. We are going to import AXI-Lite master and AXI-Lite bus. Okay, so here we instantiate AXI-Lite master. Okay. Our bus name starts with axil underscore the signals, right? So that's why like I'm giving this. Just give me a minute. So AXI-Lite master, we required bus, like instead of having every signal, like we use the bus. Okay, so we are deriving the from prefix. So from the prefix in the DUT, anything starts with axil underscore, it will use that as a bus. AXI-Lite bus. So then we have a clock. Then reset time, but this let me see if I reset tag to low. Active level will be low. Okay, so I'm putting 0. So which tells like our reset is active low. Okay, so we have waited for, like we can just after reset, what we can do is just we can wait. Let's write. We can write another value. So this is the 32-bit code, right? So we have to use write DO into the 18 register. I can write from the table. Okay. So we will go for higher rate, which is like this one. So the user value will be 54. Okay. So the user value will be 54. So now I think there is a syntax error. That's why this is the AXI-Lite master. AXI-Lite bus. we can see the AXI-Lite transactions happening. Yeah, so here we can see the AXI-Lite transaction happening. So we programmed 51. So that means in the hex it is 36. So at the okay, so sorry, this is the start address, which is yeah. Okay, I think we did reverse. Okay, so address should come first, then 54 is the actual value. Yeah, sorry for that. So since this is the higher baud rate, right? So now the time difference between each baud pulse will be less. It is like very high compared to the earlier waveform. So let us go to the waveform and reload. Okay, see, where is the yeah. So after just right after register, right, we stopped the simulation. So that's why it is again to wait. So let us wait for 2 cycles so that like we can see the actual divisor value changes. So, by this time you understood, right? I want to keep this as live as I can, so that you can see my thinking process and how I'm going to use the test-driven development. Okay, so usually this is how we do in our daily life. Okay, because uh, even a simple module also normally we don't know how to do. Okay, I mean how to do we know, but most of the stuff we do we go and check the waveforms or test driven something like that. Okay, yeah. So here at this point we changed the value. You can see the difference. Initially the divisor is configured for 9600. Now we programmed that for a higher baud rate. So you can see the baud signal now, the frequency is very high. Okay, that means like every pulse there is a transmission. Okay, that's what this higher baud rate means. Okay, so in coming sessions we can use this baud signal to transmit the, I mean to design the transmitter and transmit the values. Okay, yeah, here I can conclude this thing. Okay, so far we have designed a quadrant generator. Uh, the user is coming from the CSR module, and which we changed the value from the AXI-Lite register, and observe that quadrant generator is now generating the signal at a different value. Okay. So yeah, the coming next sessions, like in the next session, we will implement the transmitter module. Okay, and yeah, if you want to follow, you can. I uploaded the specification in the course page. Maybe you can just go through the UART specification, and I will provide the video recording there. You can go through the recording again and see how board generator design works and what are the things we did. And yeah, I will provide the Corsair tool documentation and other things. You can see my previous videos also, uh, how I use it. Yeah, and then you can do your experiment with those things. Okay, so if you come prepared by next week, maybe it will be helpful for you, so that like you can also follow the same thing and design your own. Like if you want to enhance the design, say we are not going to implement the interrupts and other things, right? So maybe after this course, you can add those things to it and gain more knowledge about it. Okay. So yeah, if you have any questions, maybe like you can ask offline or online. It's fine. Okay. So with this thing, like I'm closing this session. We'll meet next week.